This section explains what makes Spark different from MapReduce and why that single difference cascades into everything else. MapReduce writes every intermediate result to disk. Spark keeps the working set in memory across the cluster. That one inversion from disk by default to memory by default is the chapter's thesis, and the claimed speedup of roughly 100 times follows directly from it. The move that makes the whole design go through is how fault tolerance changes. Instead of replicating data, an RDD records its lineage, the recipe of transformations that built it, and recomputes any lost partition from that recipe. Persistence becomes reconstruction. Everything else follows from reuse. Streaming, SQL, machine learning, and graphs are all that one abstraction applied across modules, where MapReduce needed a separate framework for each task. There is a boundary to the game. When you touch data only once, disk still wins. Spark pays off precisely when you revisit the data, iteration, and ad hoc queries. This section explains why Spark installs the RDD as the first thing it builds. MapReduce pays for fault tolerance in disk. Every intermediate result is written out, and every chain job rereads storage. Spark's move is to hold working data in cluster memory, and to secure it by remembering how it was made rather than by keeping copies. An RDD, the chapter's first citizen, is an immutable, partitioned collection that carries its own lineage, the DAG of operations that produced it. Lose a partition, and you recompute it from that recipe, rather than restoring a replica or replaying the whole job. Redundant storage collapses into a stored program. Everything the book later builds, SQL, streaming, ML, graphs, composes on this single abstraction. That is why the chapter installs the RDD before anything else runs. This section explains why the so-called Java refresher chapter is really the groundwork Spark needs. The chapter calls itself a Java refresher, and that framing is a decoy. Its 4 topics, generics, interfaces, lambdas, and streams, are the exact minimal substrate that Spark's core abstraction demands. Here is the correspondence that does the work. An RDD simply is an immutable parallel collection over which you chain lazily evaluated operations. That is precisely what Java 8's Stream API became once the invoke dynamic instruction gave the JVM late-bound lambdas. The two are the same shade. So the chapter's real job in the arc of the book is to install a set of functional primitives, immutability, deferred evaluation, contracts expressed as functional interfaces, and type-safe generic collections. With those in place, Java can express what was born in Scala. Learn these, and Spark in Java stops reading as a translation. This section explains the one idea the whole chapter turns on, and why it let Java reach Spark at all. A function became a value you can pass. That is the whole chapter, and the whole reason Java can now speak Spark. Every Spark transformation is one thing, hand, a behavior to a collection. Before Java 8, you could not say that tersely. You wrote an anonymous inner class. 2 primitives close that gap. The lambda is dispatched at runtime through invoke a dynamic and method handle, rather than compiled into an inner class. The stream is a lazy, non-storing, chainable pipeline over a collection. These 2 are precisely the primitives an RDD is built from. Generics supply the type-safe container, and the functional interface supplies the type-safe container, and the functional interface supplies the lambda's target. Nominally, this is a Java refresher. Its single thesis is that Java 8 closed the conciseness gap that once made Spark a Scala-only language. This section explains why Spark splits every operation into two kinds and what that split buys you. A filter costs nothing. A collect costs everything. That split is the whole chapter. Every RDD operation is one of two kinds. A transformation returns another RDD and merely records intent. An action returns a value and forces the recorded chain to run. So the program you type diverges from the program that executes. You are authoring a lineage graph, and only the action collapses it into work. The directed acyclic graph, the web UI draws, and the 2debug string lineage are that same deferred graph, read statically. Recompute on failure then costs nothing extra. The lineage already is the recipe to rebuild any lost partition. Laziness buys fault tolerance for free. This section explains the single law that governs a Spark job. A Spark job is a lazy operator graph that runs nothing until you force it. Transformations, filter, map, reduce by key only extend the lineage graph. An action like collect or count is what triggers compilation. At that moment, the Spark context hands the DAG to the DAG scheduler, which cuts it into stages at exactly one kind of seam, the shuffle, where data must cross partitions. It then dispatches each stage's tasks to executors near their data. The chapter's whole apparatus, the REPL, the 4-tab web UI, Spark submit, the REST endpoints, is instrumentation watching this single pipeline resolve. Predict any Spark behavior from one law, build lazily, materialize on action, break only at the shuffle. This section explains the Spark programming model. You never tell Spark to compute. You describe a computation and hand it a trigger. An RDD is a distributed collection. Every transformation, map, filter, reduce by key returns a new RDD while running nothing, merely accreting a directed acyclic graph, a DAG of intended work. Only an action, save as text file or collect, forces the whole graph to materialize. The word count anchor is the entire model in miniature. Flat map to pair each line into a pair of the word, and the number 1 reduce by key to sum. Then one action fires the accumulated chain. The move that makes the whole model work is separating description from execution. Laziness turns the DAG into a single optimizable, recomputable object, which is also why fault recovery costs nothing, since the graph is its own recompute recipe. This section explains the single line that divides every operation in an RDD program. An RDD program is a description of a computation, never the computation itself. That is the whole chapter. Every operation falls on one side of one line. A transformation returns an RDD and merely records intent, accreting a lazy graph. Map, filter, and reduce by key are transformations. An action returns a non-RDD value. An action returns a non-RDD value, and only then pulls the entire graph into execution. Collect, count, and reduce are actions. Read an operation's return type, and you predict its behavior. An RDD out is deferred. A value out is triggering. Laziness is the architecture. The plan stays separate from its run, so it can be optimized and, through cache and persist, reused rather than recomputed each time an action fires. This section explains how Spark works with data and storage at the structural level. Spark computes but stores nothing. Every job begins by binding to an external system and ends by handing results back. This chapter is one move repeated. Whatever the origin, local disk, S3, HDFS, Cassandra, and whatever the encoding, CSV, JSON, XML, the reader collapses it onto a single carrier, an RDD or a dataset, and every transformation you write is invariant to that origin. This is the forgetful move, heterogeneous provenance mapped onto one uniform type, so computation is authored once against the carrier, never against the source. Only a thin connector varies, a text file reader, an S3, a scheme, a Cassandra utility, a format parser. All of the storage diversity is pushed into that seam. The engine stays pure. This section explains how Spark, a pure processing engine that owns no data, meets the storage world it never holds. Spark owns no data. It is a pure processing engine, and this chapter is where that purity meets the world it doesn't hold. Here is the move. Every storage backend collapses behind one call. The call JSCSC.txt file, given a path, yields an RDD of strings, whether that path begins with file ://s3, a ://hdfs:// or reaches into Cassandra. Only the URI scheme changes because Spark delegates split calculation. To HDF scheme changes because Spark delegates split calculation to Hadoop's file input format. Format is the orthogonal axis. CSV, JSON, and XML are parsers layered onto that string. RDD, never onto the reader. Location and encoding factor apart into two interchangeable coordinates, each reduced to a single swappable token. Given the pattern, you can predict the next backend without opening the manual. This part explains why moving Spark from your laptop to a cluster leaves the computation itself untouched. Nothing about the computation changes when you leave your laptop. In local mode, the driver and the executor share one JVM. On a cluster, they split into separate JVMs across nodes. Yet the driver still builds the physical plan, still schedules tasks by data locality, and the executors still cache partitions and report back. What actually varies is only the substrate beneath. It is Spark standalone, YARN, or Mesos, all addressed through one invariant command, Spark submit, with the master flag. The cluster manager is a swappable resource layer. The application is blind to which one it rides. The deploy mode flag merely relocates the driver. Client keeps it beside you. Cluster hands it to a worker. That the same code ports unchanged is the entire payoff. This section explains how a Spark cluster is organized. The whole story is one coordinator and many disposable workers. A Spark application is always a single driver JVM. The driver compiles the operation DAG into a physical plan and ships task bundles to executor JVMs by data locality. Executors are long-lived processes that cache RDD partitions and run tasks as threads, reporting back. The driver is the single point of failure. Executors are not, because the manager just restarts them. Everything else in the chapter, standalone versus yarn versus Mesos, client versus cluster mode, is one free parameter where the driver process lives and who allocates the slots. The topology never changes, only its placement. Read the cluster manager as a forgetful layer over an invariant coordinator and worker split. This section explains what changes when you move from thinking about a resilient distributed dataset as a value to thinking about its physical layout. Chapter 4 handed you the RDD as a value. This chapter hands you its physical layout. The shift this chapter turns on is that in a distributed computation, cost lives in placement rather than in arithmetic. Where a key sits decides whether than in arithmetic. Where a key sits decides whether an operation stays local or triggers a network shuffle. Partitioning is the control surface for locality. A partitioner is just the function from key to partition, and choosing it, whether hash, range, or custom, is choosing which data moves. The advanced transformations and actions are variations that respect or exploit those partition boundaries. Then come two sanctioned breaches of the closure's isolation. Broadcast variables are a read-only fan-out to every executor. Accumulators are a write-only fan-in. Locality and controlled shared state are the two levers Chapter 4 kept hidden. This section explains the 7th chapter of the Spark model, the one that hands you physical placement. The earlier chapters let you treat an RDD as a logical collection and left physical placement to Spark. This chapter hands you the placement itself. Its single thesis is that the cost of a distributed computation is data movement, and every advanced construct is one lever on it. Partitioning decides which key lands on which executor, so a well-chosen partitioner turns a network-wide shuffle into local work. Partition-level transformations, like map partitions, push code to where the data already sits. Broadcast variables and accumulators cross the boundary that a closure's private copy cannot. The generative move is this: judge any Spark API by whether it triggers or avoids a shuffle. Send the computation to the data, never the reverse. This part explains what changes when you attach a schema to a Spark RDD. An RDD is an opaque bag of Java objects. The runtime sees closures it cannot inspect, so it runs exactly what you wrote, in the order you wrote it. Attach a schema, the shape of each row, and the same distributed collection becomes a relational table the engine can reason about. That is the whole chapter. Describe the data instead of instructing the machine, and optimization stops being your job. You now write declarative SQL, and the Catalyst optimizer rewrites the plan before any RDD runs, filtering rows before a join rather than after, so less crosses the network. Data frame and dataset are just RDD plus schema. Intent: a compiler can read beats. Steps: it merely obeys. This part explains the one structural shift that Spark SQL is built around. Attach a schema to an opaque distributed collection, and it stops being a bag of records you transform by hand. It becomes a relation you query. That is the whole move of Spark SQL. The RDD is the imperative substrate, the place where you write the how. The data frame, a dataset of row, names, and types its columns, so you declare what you want and the engine's optimizer plans the how. This is declarative over imperative, the same inversion SQL always was overhand. The dataset generalizes it. A data frame is just its untyped special case. Everything else is plumbing hung around that single structural shift. Spark session subsuming the old SQL context and Hive context entry points, user-defined functions, Hive access. This part explains how Spark handles near real-time processing by streaming. A stream never becomes a first-class object here. It is made to look like one you already have. Spark slices the unbounded flow on time. Every few milliseconds of arrivals become one micro batch, and each batch is just an RDD, the batch primitive from earlier chapters. So the whole streaming engine is a thin relabeling. A D-stream is a sequence of RDDs, and the same flat map and reduced by key machinery runs unchanged. The unification is the point. One programming paradigm for batch and live, with latency traded against per batch overhead by choosing the interval. The tell is the cost. A failure replays the whole batch because the unit of work is the batch itself, not the individual message. This part explains how Spark handles a continuous, unbounded stream. A continuous stream is tamed by refusing to process it continuously. Spark streaming slices the unbounded flow into micro batches keyed by a time interval. Every message arriving in, say, 1 second becomes an ordinary RDD, and a sequence of these is a D stream. The stream never meets a new engine. It is fed, batch by batch, to the batch engine already built. That is the entire move. Discretize the unfamiliar into a sequence of the familiar. And every operator you already have, core, Spark, SQL, MLlib, composes over it, unchanged. Latency is the price, bounded by the interval length. The reward is one paradigm spanning offline history and live present. That is the chapter that makes Spark general purpose, a tool for far more than batch alone. This section explains how machine learning on a cluster collapses to one algebra over a single data type. Everything is a data frame. Feature vectors, labels, and predictions are all columns of the same table. Every learning step is one of exactly two morphisms on that table. The first is a transformer, a map from data frame to data frame. It adds a predicted column, binarizes or extracts features. The second is an estimator, whose fit method consumes training data and emits a transformer, which is the trained model. Cleaning, feature extraction, training, and validation stop being distinct machineries and become composable stages. A pipeline is just their ordered composition. That is the whole chapter's thesis. Spark 2.0 moved machine learning from RDD imperative loops to this Spark.ml composition of two morphism kinds, distribution and iteration. Hide beneath function chaining. This part explains how every machine learning step reduces to just two kinds of arrow over one shared object. The data frame. Every machine learning step collapses to one of two arrows over a single object, the data frame. A transformer takes a data frame and returns a data frame. It appends columns through its transform method, whether that is a tokenizer or a trained model tagging predictions. An estimator takes a data frame and returns a transformer. Its fit method consumes training data and hands back a transformer. Learning is only that second arrow, and the model it returns is itself the first kind. A pipeline chains them in order and is itself an estimator. Its fit method folds the whole sequence into one composite transformer. Here is the author's compression. The machine learning package is a set of user-defined function operations over the data frame. Now predict the rest. Extraction, scaling, and selection are all transformers. Anything that must train first is an estimator. This section explains how Spark GraphX builds a graph. A graph in GraphX is two RDDs wearing a relation, one of vertices, each a pair of identifier and property, and one of edges, each a source, a destination, and a property. That single reframing is the whole chapter. Because the property graph is a pair of RDDs, every RDD guarantee transfers for nothing, partitioned, immutable, fault, tolerant, lazily evaluated. GraphX adds no engine, it adds only a lens. The lens's sharpest move is the edge triplet, an edge that has joined its endpoints properties so a relationship can be reasoned about knowing both ends at once. Split vertices from edges, and you may transform one without touching the other. Everything downstream, page rank, triangle count, is just algorithms reading this join. Graph computation reduced to relational reuse. This section explains why a graph in GraphX is not a new engine. A graph here is a pair of RDDs, one of vertices, one of edges. That single move is the whole chapter. Because the property graph is just those two datasets, it inherits everything the RDD already is for free, partitioned, immutable, fault-tolerant, lazy. And every graph operation collapses into an RDD transformation you already know. Map vertices is just map. Subgraph is just filter. And aggregate messages, the primitive that counts a vertex's followers, is send message and merge message. Word count on edges, map, reduce, wearing graph close. Here is the chapter's place in the book's arc. Graph X adds no distributed computation idea. It reprojects the Chapter 4 RDD as relations. Graph analytics is a view, not a substrate.